Let's look at solutions for the range minimum query problem. And let's start simple. So let's first think about the simplest possible ways we can do this. I think there's two trivial solutions that don't require any insight or any thought, but they're still helpful to write down because they show the two opposite ends of the trade-off between pre-processing time and query time. The arguably simplest one is don't do any pre-processing, just do nothing at the pre-processing time. And whenever you're asked for a range minimum query, you just scan through this array, keeping track of the minimum, and then you return the position where you found it. So I would go and scan from the beginning. 6 is the current smallest I've seen. Oh, then I update it to 3, and I keep track of the position. No better one. Oh, this is actually smaller, so I keep track of it. Keep going, keep going, keep going. I don't see a smaller one than 2, so 10 remains my answer. This is clearly fine, but it's very slow at query time. We have to spend linear time at the query if we don't pre-compute anything at pre-processing time. One end of the spectrum. The other extreme is pre-compute everything so that the query time just becomes a trivial lookup. But that blows up the pre-processing time a lot. The simplest thing you can probably think of is to store an array with the answer given every possible combination of I and j. So the query is just returning that value, but of course you have to fill all those values. If you compute all those values, so we start with, well, I can be anything between 1 and n, and j can be anything between I and n. So that's roughly n squared over 2 entries. So that's that many entries that we have to compute. If we just use the simple scanning from before, we get another factor of n, which makes this cubic. But here's a simple observation. If we currently have computed the range I up to j, I can go to j plus 1 with a single comparison. I can just take the minimum from the previous range, and I just computed it. I stored where that is. I can just compare those two guys, and then I know the minimum of I up to j plus 1. So if I'm not completely stupid in ignoring all that I've pre-computed, I can do the pre-processing in quadratic time, so spending constant time for each entry. Remember what I said before, the space here obviously is quadratic. We need this 2D vector that has n squared over 2 entries. And we can also fill those entries in the same time. So time and space here are of the same order of growth, the same magnitude. Those are the two trivial solutions that immediately come to mind without much thought, but both are not very interesting. The first slightly interesting solution is called the sparse table. And the idea is to take the pre-compute all solution, but get rid of most of the entries in this gigantic array, and only keep some of them, but just enough so that queries are still fast. How should this be possible? Well, the solution is to take keep entries for every starting position. So I still runs from 0 up to n. But then the allowable entries for j, where we actually store something, are only powers of 2. Okay. So we would probably store these entries differently. We would probably store them by using this exponent as our index. Then for every starting position, we have an array with all the exponents up to n, so that's just log n entries. And we have that n times. that's how you get to n log n entries. Okay, that's a definition. It doesn't tell you how you can make use of these entries to answer any query. The queries are not restricted. We can get any I and j combination. We have to still be able to answer all of those. How are we doing? How are we able to do that? And at that point, it becomes important that this is a power of 2 and not just an arbitrarily selected subset of the entries. Whenever you have a range from I to j, you can compute its length. Say that's L. That's the same I used here before. Now, we can always find a power of 2 that is between half of L and L. Sometimes there might actually be 2 choices. If L itself is a power of 2, then we don't really care. But we can always do this. So we can always, maybe I should say this also in the notes. Sorry, I can always find a k with this property. And then we'll use 2 queries. One that goes from the left end, I up to I plus 2 to the k minus 1. And the other one that goes left, it starts at j, or it ends at j really, sorry. And it goes up to j minus 2 to the k plus 1. And in that way, the way we chose k, those two at least touch, or well, those two cover the entire range I to j. They might not overlap in case we're at the lower end. They might exactly touch, but there's definitely no element that's not covered by either the green or the blue range. And also, these don't overshoot. They're entirely within the red area. All right. So we can always find such a k. And then the range min query of I to j is just the position, the smaller of these two subqueries. Well, let me just take the blue RMQ and the green RMQ. They're really, well, I can write this in a second. I don't want to make the formulas more cluttered than necessary. So the blue RMQ is of course nothing but the RMQ with the blue range. So it goes from I to I plus 2 to the k minus 1. And the green range is the other one. J minus 2 to the k plus 1 up to j. So the minimum in the entire range is, it must be in the green range or in the blue range or in both. It can't be outside all of those. So by comparing the green and the blue minimum, definitely the smaller of the two will be the global minimum. And that's what RMQ asks for. All right. This shows that by going from n squared to n log n entries, we can still do queries in constant time. All we have to do is look up 2 answers, the green and the blue one, and compare the entries at that position and return the one where the array entry was smaller. That's all we have to do. So I don't want to forget to check. Okay, that was just the warning for Pingo. All right. So the number of entries is n log n. You can also fill these in constant time per entry. And that is if you go from a range I up to I plus 2 to the k minus 1, and now double the range, 2 to the k plus 1 minus 1. Well, you can find another position, namely I plus 2 to the k, so that, again, roughly the same picture as here happens. You have a green and a blue part. And if you compute the table with increasing k, you can use the two previously computed parts, compare the minima wherever they were, and the smaller of those two is the minimum in the entire range. So again, every entry can be filled in constant time by looking up two previous solutions and comparing the minima at these positions. So that gives us a solution with constant query time and n log n pre-processing time. So interestingly, up to now, there has been not at all any trade-off between pre-processing time and query time. We could keep the perfect query time of the stupid compute everything up front solution and just knock down the pre-processing time to n log n instead of n squared. That's pretty cool and also pretty useful, because this is already useful enough for a longest common extension data structure.